Hello, this video is called The Basic Concepts of Probability. It's section 3.1 in the Larson book, so let's take a look at what we've got here. Now we're going to start out with some kind of terms here that are used in probability. Probability experiment, outcomes, sample space, and events. So probability experiment, so like it defines here an action or trial which results in specific measurements, things, like flipping coins, rolling dice, spinning roulette wheel, all kinds of things like that are considered probability experiments if you're trying to measure the results or outcomes from that experiment. And the result of a single trial of an outcome of a probability experiment is called an outcome. So let's say you're going to flip the coin 10 times and record heads or tails. Each one, there'd be 10 individual outcomes. The set of all possible outcomes for a probability experiment is called the sample space. And an event is a subset of the sample space. And it may consist of one or more outcomes. So for example, if you roll a single six-sided die, your sample space is going to be, when you're counting the number of dots facing up, the sample space will be 1, 2, 3, 4, 5, and 6. If you flip a coin, sample space will be heads, tails. Now let's look at the examples of events rolling a single die. Yes, die is actually the singular word for dice. So let's take a look at this. Let's define an event E of rolling a 4. We're rolling a 4, it's just going to be that one number 4, that's called a simple event because it's just one outcome. Now the next one says, suppose we define event F as rolling a number divisible by 3. Well, in the numbers 1, 2, 3, 4, 5, 6, you have two of them that are divisible by 3, 3 and 6. So we call that a compound event because there was more than one outcome. And same thing with this next one, it's also compound. Rolling a number less than 3. 1, 2. All right. Let's say you flip two coins and you want to write the sample space of all possible outcomes. Now for two coins, it's not too hard to list it out. You can just, you can go head, it can be heads then heads, heads then tails, tail, heads, and then tail, tail. 4 possible outcomes. And that's the same whether you're flipping one and then the other or flipping them both at the same time. Now, for 3 coins, it probably helps to do what's called draw a tree diagram and follow the path. See, for the two that we just did right here, you could stop at the second branch and then you follow the paths, H, 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 T, and that's how you can come up with this. But you can go heads or tails, then off every branch you can go heads or tails. So head, tail, all bunch of head, tails, tail, tail, head, tail. And then you can list them out. Just follow the paths. H, 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 3 heads in a row. H, H, T. HTH, HTT, so forth, so on to build this list. With 3 coins, you could probably do it without the tree diagram, but it would be maybe, you'd have to think about it a little bit more, like which one to come up with the list. But following that tree makes it easy. Then, you can keep extending that tree, but we don't want to get that creative. But yeah, you keep going to more tosses, and it just gets a little bit long, unnecessary, I think. So let's talk about something here called the fundamental counting principle, and then we'll see what that's all about. Now, the number of outcomes occurring in sequence while you're choosing one of each outcome is calculated as just multiplying the number of outcomes times each other. Now, it says N1, N2, N3, ... means, so forth and so on. Now, suppose someone wanted to wear an outfit and they're choosing, one of each of these. In other words, one dress, one pair of shoes, one purse, and one pair of earrings. Now, we are having to go under the assumption that all of them are coordinated, which I don't know anything about that, but we assume that you can wear any combination here without, and it'll still be fashionable. So the number of possibilities is just multiplying 20 times 50 times 15 times 20. So that means there's, assuming all things can be worn, 300,000 different possibilities of choosing one of each. Boy, that sure seems like a lot, doesn't it? Let's take a look at this example. Choosing a 4-digit PIN code, 0 through 9. Now keep in mind, 0 through 9, you can count that up if you want to, but that's 10 digits, not 9. I see people make that mistake. With repeats, without repeats, and then number C is part C. We'll get to that one in a minute. Let's do the first two. With repeats, it means it can be any one of the 10 numbers first time. Then 10 again, 10 again, 10 again. So it's 10 to the 4th. So that means there's 10,000 possible PIN codes. Now, if you can't repeat, that means all 10 of them are available the first time. But whatever you chose the first time is not available the next time. So it goes down to 9 choices. Then the first 2 are not available for the next one. So you're down to 8 choices, so it just keeps decreasing by 1. And then the last one, none of the first 3 are available, so there's only 7 left. So 10, 9, 8, 7 equals 50, 40. Just multiply that out in the calculator, nothing to it. Now the next one, a little tricky. It says cannot begin with a 0 and must end with an odd number. Doesn't say anything, so if it doesn't say anything about the other positions, you would assume all numbers are available. 9, because you can't use 0. All 10 for the second one, no restrictions. All 10 for the third one, no restrictions. The last one would have 5 because in the numbers 0 through 9, you have 5 odd numbers. 1, 3, 5, 7, 9. So that's what makes that number 5, and that ends up being 4,500. Now here's one we have license plates that were just strictly said, okay, it's only going to be 3 letters followed by 3 numbers. So 3 letters, 26 letters in the alphabet. So if you're allowing repeats, you could have any of the 26 letters, 26 again, 26 again. Then you go to the digits. So it's all multiplied together. And they're not 2 separate problems. They're just 2 separate total number of things you're choosing from. So 26, 26, 26 times 10 times 10 times 10, meaning they can all be repeated. And there's your result right there. And the next one, no repeats of letters. When it says no without repeats, you can assume that means both letters and digits. If it only meant one of them, it would need to specifically say that. So 26, we lose a letter. Down to 25, lose a letter. Down to 24, we start fresh with the digits. All 10 digits are available. Drop down 1 is 9. Drop down another is 8. And there's your result from that. There we go. Okay, not too bad. 3 basic types of probability. First one's classical or theoretical probability. It means it's calculated as the number of outcomes that are in your event E, and then the total number of outcomes in your sample space S. And fraction, or it can be written as a decimal, which can then be written as a percent. So like I'm defining an event T as flipping a tail. Well, if you have there's one way you can get a tail when you flip one coin, but there's 2 total outcomes, heads and tails. So it's 1/2. You've got a 1/2 or a 50% chance, 0.5, that you would flip a tail. And it's the same thing for heads also. It would be 1 out of 2. Now, suppose we're defining an event as rolling a 3 on a single 6-sided die. Well, there's only one number that's a 3, so there's 1 on top and then 6 on bottom. So you're dividing by 6. 6 total numbers on the die. So it would be 1 out of 6. Now, this one rolling a number less than 3, this would be a compound event because there's 2 numbers less than 3, 1 and 2, so you have 2 ways to do it. divided by 6. So you see it still divides by 6, or, you know, if you're looking at answer choices, it may go ahead and reduce the fraction. It doesn't mean the 1/3's not any more mathematically correct, but it's just a reduced fraction. But it's 2 out of 6, which then reduces to 1/3. All right, empirical, or what's called statistical probability. This is essentially the calculation for relative frequency based on a measured amount of results. So it's the frequency of your event divided by total frequencies. Like this example says, suppose we flip a coin 100 times and record the results. And we got 56 heads and 44 tails. From this experiment based on measured results, we would say the probability of obtaining a head is 56 over 100, and the probability of getting a tail is 44 over 100. So it's just based on, like this example. We have 4 different majors. The frequency, suppose we just surveyed 50 people and they were only out of these 4 majors. And you said, okay, what would be the probability that you select a nursing major out of that group? There are 8 nursing majors divided by 50 people total. So you would have probability, you know, 8 out of 50 is correct, 0.16 is correct, 16% is correct. So essentially it's just 3 different ways to express the same value. All right, hopefully we're having fun so far here. Subjective probability. It's based on personal feelings and not really a calculation. Now however, you have you're restricted, and we'll talk about, as I mentioned here, you'll see this definition below. But when you calculate a probability as a fraction or decimal, the answer's got to be between 0 and 1. As a percentage, it would be between 0 and 100%. I'll go ahead and scroll down so we can see all that on the screen. So there it is. As a percentage, it has to be 100. So this is not based on any kind of data or anything. It's just, it still has to be between 0 and 100. You go, all right, I think before you start this class, you might go, I think I got about an 80% chance of making an A in a statistics course. But there's no, you know, way to discredit that or anything. It's just your personal feelings. However, if somebody were to say, I've got a 110% chance I'm going to make an A in a statistics course. No, you don't. That's impossible. Just like when someone says they're giving you 110% effort, impossible. 100% max. So now you know that whenever somebody says that, I gave it 110%. No, you might have given it your full 100%, but you can't give more than what's available to give. So long as the number's between 0 and 100, this isn't something you can really disprove or anything like that. So this will be very important on the range of probability. So if you're working some sort of probability problem and you go, I swear the answer is 1.2, I know it is. It's not. It cannot. It's got to be between 0 and 1 when it's in regular number form, not percent. Now this is a term that may pop up here. You know, we'll see maybe in a homework question or something. I generally don't use it on a test question, but it might pop up in homework. An event that occurs with a probability of 0.05 or less is considered an unusual event. So, like if there's a problem, and you know, some of these problems in the homework will have sometimes, you know, multi-parts, and you calculate a probability, and then in the next part it directs you to may say, oh, is this considered to be unusual probability? You're just looking to see whether or not, if it's less than 0.5, you say yes. If it's not, you say, it says 0.5 or less. So actually you include 0.5. If it's bigger than 0.5, then you would check the box that says no, it's not unusual. So here's an interesting question here. Which of the following cannot be a probability? 50% is okay. 0.0001 is okay. Exactly 0 is okay. Let me come back and talk about this a minute. We say, and I'll show you an example of this in a minute, but you can have exactly 0. That means no chance it occurs. And you can have a probability of 1, which means it's a certain event that it's a 100% chance it's going to happen. And you go through this list, 5 over 4. Not between 0 and 1. Actually, it's 1.25. It has no chance of being the right answer. Now the next one, everything's good. 1's okay, 0, 0, 0, 5's okay, but there's your killer on the last one there, and can't be negative. You can't have a negative probability. So here comes an example of where you can get the no chance and the certain event here, how they can occur from an experiment. So let's say you roll a single 6-sided die, and it was asking you, okay, what's the probability of rolling a 7? Well, there are no 7s. So essentially, formally, it would be 0 divided by 6. But 0 divided by 6 would equal 0. So the answer would be 0. So that means basically no chance. Now the next one says find the probability of rolling a number less than 7. Well, 1, 2, 3, 4, 5, and 6 are all less than 7. So that's 6 of them. And then 6 out of 6. 100%. That means that's a guaranteed. You roll a single 6-sided die, you have 100% absolute certainty you're going to get a number less than 7. Guaranteed. So there's how you can reach the two extremes of 0 and 1. Standard deck of cards. Don't worry if you're not familiar with this. You don't have to be a card wizard or anything here. We're going to show you what you need here. You don't have to know anything about card games or anything. But just be able to use this deck to answer probability questions. And I want you, so I think you'll have no problem learning this for what you need to do. So we're not training you to play blackjack or anything like that. A standard deck of 52 cards has 4 suits: hearts, diamonds, spades, and clubs. Kind of makes me think about Lucky Charms cereal. I'm too old for that much sugar anymore now. Well, it was great when I was a kid. Anyway, there are 13 of each one of those. So then 4 times 13 makes 52. And hearts, because it's hard to tell from this color, the way this came out in the notes here, but those are red. I promise you, they're not pink or purple. Those are red cards. 13 red hearts, 13 red diamonds. It's even hard to tell from that picture, too. I don't know what. Okay. I promise you they are red. And the spades and clubs are black cards. So basically 26 of them are red, 26 of them are black. Now the A is called an ace. J, Q, K are called Jack, Queen, King. Those are also known as face cards. You can't see the other two here, but they are called face cards because there's somebody's face on them. That's the real reason. The Queen and King also have faces on them. I believe the deck of cards is kind of attributed back to, I believe, the French people way back when or whatever, so kind of sort of has a little royalty thing to it there, so. So we just want to be able to answer probabilities questions on here. We select one card at deck from at random. Find the following probabilities. Probability you select is 6. So notice one thing off the bat. Your sample space is 52 for every one of these. So it's going to be something out of 52. And, the fraction, of course, may reduce, but it starts out as something over 52. So that's not a problem. When you're picking an answer off of a test. I'm not sure what they're going to want in the homework. If they'll want decimal, whatever they want, we'll do whatever it tells us to. With test, you might see the reduced fraction. If I showed you an example over here in the calculator, if you go 12 over 52 and go answer frac, it'll reduce the fraction for you. So we know it's still out about 52. We want to know how many 6s do we have. We have 4 6s. 2 red ones, 2 black ones. We have 4 6s. 4 divided by 52, which reduces to 1 over 13. What's the probability of selecting a heart? Okay, well, there are 13 hearts. So it's 13 out of 52. And that reduces to 1 over 4. Probability of selecting a black card. We have 2 spades and clubs, 13 each, that are black cards. So 13 plus 13 will be 26. So it's 26 out of 52, which reduces to 1/2. So you basically have a 1 in 2 chance you'll pull a black card out of there at random, which kind of makes sense, I think, because half of them are red and half of them are black. So, and face card. Once again, the face cards are Jack, Queen, King. Here they all of them are listed out right there. But you can look at it as 4 Jacks, 4 Queens, 4 Kings. That is 12. 12 face cards. So it's 12 out of 52 and reduces to 3 over 13. The next definition here is called the complement of an event, E. Complement. It's not the same kind of complement as, my, that's a lovely hat you're wearing today. That word's actually spelled with an I between the L and the M. And this idea, complement, means not something, the opposite of something. So it's the set of all outcomes in a sample space that are not included in E. So if you define what event E is, the complement means not in E. And it has E, it's denoted with E with a single little quote there, which we refer to that quote as prime. So anytime I say like E prime or F prime or whatever, yeah, E doesn't have to always be your event. You know, it's one of the standard letters used for an event. Just the only letter you would never want to use is S, because S always means sample space. But, you know, you could have event E, event F, event H, you know, any kind of letter you want, just not S. Now, you can calculate the probability 2 different ways. This formula, the probability of E is 1 minus the probability of E prime. Or then the same thing, the probability of E prime is 1 minus the probability of E. So let's look at these examples. So in other words, kind of give you in percent form. For example, let's say, okay, the probability it's going to rain today is 60%. Well, that means the complement, which is the probability it's not going to rain, is going to be 40%. In other words, 100 minus 60. So it's 100 when it's percentages. When it's just fractions or decimals, it's 1 here. So now roll a single die. We're defining E as rolling a 6. So what's the probability of not rolling a 6? Now that one's easy enough where you could probably just go through and count, you know, the ones that are not 6. But here I'm using it to illustrate the formula, so that we know that rolling a 6 is 1 over 6. But so it's 1 minus 1 over 6, which equals 5 over 6. But if you're wondering, could I have just gone through and counted not a 6 as being 1, 2, 3, 4, 5 values? Yes, that would have been right also. That would have been okay. I'm just trying to illustrate the 1 minus. So what's the probability of not drawing a heart from a single deck? That would be the same as 1 minus the probability of actually drawing a heart, which we did. I think we did that up here. Yeah, B on that example. So it's 1 minus 13 over 52. So you have a 39 over 52 probability, which reduces to 1 over 4 of not drawing a heart. All right. So this one, probability of winning a prize is 0.12. What is the probability of not winning the prize? It would just be 1 minus 0.12, which is 0.88, excuse me, 0.88. It's correct as written there. Now let's talk about something called the law of large numbers. And the law of large numbers is what connects empirical probability to theoretical probability. They kind of make a connection. Now, an experiment is repeated over and over and over. The empirical probability, which is the measured results, approaches the theoretical or actual probability of an event. Now, I'm giving you an example here. like say, suppose you flip a coin 10 times, you could get like 9 heads and 1 tail, which for that few of number of tosses, that's not unreasonable. Each time you toss it, theoretically, there's still a probability of 1/2, each time. Yeah, but the empirical probability in this case would be 9 out of 10 for heads and 1 out of 10 for tails, which is not going to be the long run probability. But this says if you flip a coin a very, very large number of times, at least 1 million, some people argue even higher than that, then you're expecting the results to be extremely close to half heads and half tails. Let's say if somehow somebody was able to simulate, which one person really couldn't do this because it would take too long, but just humor me with the idea here, that if somebody was able to simulate 10 million coin flips. That doesn't mean you're going to get exactly 5 million of each, but they should be close. But if it's flipped 10 million times and you got 9 million heads and 1 million tails, that tells you there's something wrong with your coin. 9 out of 10 means nothing. Flipping these 9 out of 10. 9 million to 1 million, your coin's messed up. It's like maybe it's got some different metals in there that weight it funny or whatever the case may be. It's not an unbiased coin at that point. So it should even out in the long run is what we're saying. So let's take a look at this, some more counting examples here. With probability then. Access code is a letter followed by 4 digits. Any letter can be used. The first digit cannot be a 0 and the last digit must be even. So we're assuming digits, 0 through 9. You can assume that unless it says otherwise. Any letter, 26. First digit can't be a 0. So that means it can be anywhere 1 through 9, which is 9. It says nothing about the next 2 numbers. So all 10 are available for the next 2. The last digit must be even. Now keep in mind 0 is not an even number. So the only even numbers that are 0 through 9 are 2, 4, 6, and 8. So there'd be 4 of them. 93,600. What is the probability of selecting that correct access code in the first try? Now, of course, the assumption here, which would be pretty much common sense, it would have to tell you if there was more than one correct access code, but you would assume there was just one. So you would have a probability of 1 out of 93,600 chance of guessing it. And then what's the probability of not selecting on the first try? So not is the complement. That means 1 minus 1 over 93,600. So you would end up with 93,599 over 93,600. So obviously you have an extremely high probability of not guessing it. And in probability terms, when we say high probability, we mean a number close to 1. And when we say low probability, we mean a number close to 0. We'll look at some homework here in this 3.1. Pick out a few here that I think look kind of interesting. There's quite a few that I think that are very easy based from the notes and whatnot. So this one's not too bad, but it could maybe kind of throw you off a little bit. You've got 6 questions, true, false. So it basically is that multiplication fundamental principle of counting that we saw in the notes there. It's the same kind of idea, but you would look at it as true, false, meaning there's 2 answer choices. So what does it mean for that? It's essentially it's going to be 2 times 2 times 2. You have 2 choices every time. I'll just put ... because it's essentially going to equal 2 to the 6. So because there's 6 questions. So for true false, it would always be 2 raised to whatever the power of the questions are. All right, 2 raised to the 6th, 64. And obviously, you'll maybe get a different number of questions or whatever when you do this. So 64. Wonderful. All right, that's not too bad. I might leave that one, or I might come back to it. I don't think classical, theoretical, classical, empirical, subjective shouldn't be too bad. Let's look at this one. Frequency distribution over there to the right. This pretty much has to add up to, oh no, it doesn't have to add up to any specific number, excuse me. Let me dump this in Excel. So we have the values, and let me go ahead and sum these up. Oh, enable editing, okay. Now I can sum these up. Now, there's a couple ways you can go about this. Notice it says that question says not, probability not between 35 and 44. That means you can take everything that's not in 35 to 44 and add it up. Or you can use the complement and say 1 minus what is in 24.1, 35 to 44. So I can go, that's the way I'm going to do it. So I'll just pick a cell over here and I'll do the formula text so you can see what I entered for sure. I'll put E5 right next to it. Nothing's in there yet, of course, but I'm going to say equal 1 minus the what's in the 35 to 24, which, oh, I should have done that. Well, B5. And then I can just put the 141. I could have put the number in there, obviously, but either way. So I basically just did 1 minus of what's in there. So it should be 8.2. How many decimals did it want? 3 decimal places. Well, it was 8299, so that's going to be 830. And you can format it yourself if you want to. Format cells, number, and then right here you can tell it how many decimal places you want. There we go. If you need that. 0.830. Wonderful. All right, Jim Locker, 3 digits. Each digit 0 through 5. So it's specifying. If it just says digits in general, you would assume it's 0 to 9. Anything else they have to mention. Digit can be repeated. So what's the probability of selecting it correctly on the first try? Well, we're assuming obviously that there's 1 digit, 1 correct. I'm going to put this in alpha y equal to put it in fraction form. 1 divided by, there's 6 possibilities on the first digit, 6 possibilities on the second, and 6 on the third. So it's 1 over 3 sixes multiplied together. 3 decimal places. I believe we can go math and choose decimal here to convert it, or you could just retype it. I think it should work. Yeah, it wants 3. So 005. Excellent. Probability of not guessing it correctly be 1 minus 0.005. Oh, the wrong minus. Pay attention to what I'm doing here. 995. Well done. Let me look and see how many we have here. It's kind of the same. Yeah, this number 11 shouldn't be difficult. All you got to do is highest, maybe more parts of this question, but is a doctorate, is look how many doctorates there are, which is A, 3, and then divide it by you just add up all those bars and divide how many you have out of that. So it's going to be 3 out of, I guess I could do it real quick. I'll just do this in my head real quick. 3 24s, 27, 30, 60, 80, 85, 87. So let's try 3 out of 87. Thousandth, which is 3 decimal places, would be 0, 3, 4. Well done. So even though this has a few more questions than maybe some of the other assignments, they can be done a lot quicker. Unusual, that's in the definition in the notes. Unusual means anything that's a probability of 0.05 or less. And it says if any of the events can be considered unusual. So other would be considered unusual. Yes, because at least one event has less than or equal to 0.05. All right. Pie chart. Okay, they got all the numbers there. So what is this one? Find the probability was not employed in the service industry. So you can do this one of 2 ways. You can use the 1 minus. You can do service industries right here divided by adding up. So it's got all the numbers there. There's the number. They couldn't fit it in the picture, but there's the number for that wedge. Here's the number for that wedge. So you'd add all 4 of those up to get your total. So you can do 1 minus the service amount over the total, or you can add up the 3 individual pieces and put that over the total, and that would be the same thing. Oh, stem and leaf. Let's try this one. I want to do this one. All right, team selected at random. Find the probability that team scored at least 31 touchdowns. Now, we talked about this back in the stem and leaf. It's kind of a similar question that we asked back then. We just hadn't defined it as probability. We used the word proportion, I believe, what proportion or whatever. So now, how many values do we have here? You can count on the leaves. Remember, the number of leaves tell you how many total numbers there are. 6 and 11, 17 makes 17. That's 18. Makes it 35. 35 plus 15 is 50. Hope I'm doing this right. 57, 61, 62. I'm doing this kind of fast. Find the probability that the team scored at least 31 touchdowns. So I got 62 leaves when I counted that up. At least 31 means you start right there where that 1 is on the row where the 3 is. You start with the 1 because that'll be 31. So how many leaves are there? I think I'm going to snip this out and put it on a scratch page here. So I'm going to write the 62 down here. So it starts right here and goes down to there. So there are 5, 10, 16, 5, 5, 10, 16 here. 7, 4, 1. So 32, 43, 44. Let's put that in the calculator. And what's the rounding? 3 decimal places. So 7096 would be 710. I probably miscounted. Dang it. Okay, I paused the video and recounted, and my denominator was wrong. There were 63 total entries, not 62. So I changed it to 44 over 63 and got 0.698, and that was correct. All right, so between 40 and 49, so everything's going to be out of 63. 40 and 49, how many do we have on this row? I'll do them in blocks of 5. 5, 10, 16. So let's try 16 out of 63. Uh, 254. Excellent. More than 72. Well, there's only one number down here, 87. That's more than 72, so that's going to be 1 out of 64. .016. And are any of these events unusual? The last one would be, because that is a probability of less than 0.05. So scoring more than 72 we would consider to be unusual by that definition. All right, well, that concludes this video, 3.1 Basic Concepts of Probability.